Hi, my name is Jasim and this is my EMAF assignment video presentation. In this video, I will be covering the Euler formula. The Euler formula is a method which uses the differential formula to predict future values of y by increasing the x value in small constant increments known as the step size. It is used when we do not know the original equation of the graph, but we do know the derivative, also known as the gradient. I will use this line graph to help you guys visualize. As you can see, the first coordinate is 0, 0, but what we are trying to find is the value of y when x equals to 1, which we will call y1. There is a way to find this value without needing the general equation, and that is using the Euler formula. Now we are given the derivative, but not the general equation. The derivative represents the gradient, which is represented by the rate of change of y with respect to x, which can also be written as y1 minus y0 over x1 minus x0. This equation can be manipulated to make y1 the subject of the formula. This is essentially the Euler formula. In short, it finds future y values by multiplying step size with the last derivative and then adding the previous y value. For this example, I chose 1 as the step size, which means we are jumping straight to the coordinate we are after. I will explain why we can't always do this in a bit. First, we add 1 to our current x value. This will give us our x1. Then we plug in the necessary values into the Euler formula to get our desired y value, which is known as y1. After fact checking with the general equation, you can see that both the values match. However, this is not always the case, since the gradient remains the same in this straight line graph. In this curve, for example, the derivative value is dependent on the x value, which means it will be constantly changing. Our step size must be small, as we are using the gradient of the previous point to predict the next y position. Graphs like this, where the gradient is constantly changing, a big step size will give us an inaccurate value at the end. By having a small step size, we are able to follow the curve very closely and watch how the gradient changes slowly, allowing us to get a more accurate prediction. The desired y coordinate at x equals 1 is 15. As you can see, the second table, which had a smaller step size, gave a closer reading to the original value compared to the first table. I know it's quite far off, but we can always decrease the step size to get a more accurate value. It will never be on the dot, unfortunately, for some complex graphs. Now the equation I'll be solving has a derivative x squared plus 1 over y, with the initial y value being 1 when x is 0. Using the Euler formula, I will be finding the approximate value of y when x is 1. So I made 3 columns. The first column consists of the x values, which starts at 0 and will be increasing by 0.05 each step. The second column represents the y values, which starts at 1, and the future values will be found using the Euler formula I explained earlier. The third column represents the derivative at each step, which is x squared plus 1 over y. The Excel formula I used for each row in the first column is basically the previous x value having 0.05 being added to it. For the second column, I multiplied the previous derivative value to the step size, which is 0.05, and then added the previously found y value as per the Euler formula. For the third column, it's basically keying in the x and y values in the same row into the derivative formula x squared plus 1 over y. After keying in those 3 formulas, all I had to do was drag each column down one by one, and Excel's autofill feature keyed in the formula to the rest of the cells automatically. In order to check our accuracy, I had to find the general solution. I had to solve the differential equation by separating the variables, integrating both sides, solving for c, and manipulating the equation to make y the subject. After subbing in x equals to 1, the y value I got was 1.9149. Comparing with the Euler solution, there's only a difference of 0.002, which shows the Euler method was very close to the actual value, proving its ability to predict positions. And with that, I've come to the end of my EMAF assignment video presentation. Thank you.